Now, our next keynote is on Professor Agrawal, and he's from New York and also the editor of the Journal of Bridge Engineering. And we can start your presentation.
Thank you very much, Professor Caner. Can you all see me, see my screen and the PowerPoint?
Yes, we can see your screen, definitely.
Okay.
I think it was your daughter on your desktop.
Excuse
me? Yeah, go ahead, sorry.
Yeah. All right, so let me, one second, let me go to the next screen. It's better that way. Let me stop sharing and I'll share another screen. So. All right, so thank you very much for this opportunity to make this keynote speech. The topic that I'm going to talk about is vehicular impacts on highway bridges. We'll talk about impacts on bridge piers, and if I have a time, then I'll also talk about impact on overheight impact, on girders. Some of the work has been, in fact, good amount of work that I'm presenting has been in partnership with Dr. Ran Kao, my former PhD student, who is back to Hunan University in China right now. And Dr. Sharif Al-Tawil, you might know very well, he's at University of Michigan and had been the, chief editor of the Journal of Structural Engineering. He just finished his term in October, and till October for 10 years, he was the chief editor. Also, a good part of research that I'm presenting here has been sponsored to Federal Highway Contract on Hazard Mitigation team with Mr. Waida Wang as our task manager. Some of the work on vehicular impact on bridge piers that I'm presenting was published in the Journal of Bridge Engineering of Vehicular Impact of Bridge Piers. And this paper was actually awarded the 2020 Arthur M. Wellington Prize by ASCE. Objective, generally, I'm going to talk about vehicular impacts on bridges and kind of like a developed guideline to achieve a desired performance level during heavy vehicular impact, a method to predict impact loads based on weight and velocity, performance levels, approach to achieve a desired performance level, and examples and effectiveness, how the method works. But let's look at what is exactly the vehicular impact. So we designed the bridges for gravity and live loads. But sometime in the life of the bridge is subjected to one of these extreme loads, hydraulic overload, collision, earthquake, and may lead to failure of the bridge. Now, if you look at all the impacts, all the causes of failure in USA in the last 20 or 30 years, then of course hydraulics is the biggest one. We do a lot of work on seismic, but there had not been a major earthquake in US. So, damage to bridges because seismic has been much less actually. All others are 14%, but if you look at the specific cause, then collision, the collapse of bridge because of collision is actually one of the leading causes, in fact, prominent causes. Overload is of course another cause, but collision is one of the leading causes of a bridge collapse. We did this survey in 2011, all the states in USA to find out how big is the collision a problem. And collision included overheight impact mostly, but some states also included pier impact. So if you say all the red areas, these are like a major problem. Green areas, minor problem. Some did not respond there in yellow. And numbers are there, which are on the 4-year period between 2008 to 12, I think. But number doesn't matter because if you look at Missouri, 1691 incident of impact and they say minor problem. Florida, 195, they call major problem. But overall, across the country, this has been a major problem when the trucks hit the bridge piers or superstructure. In fact, this is very interesting video of a police chasing a truck driver because he's on the parkway and there's a low overheight bridge ahead. and he's trying to stop the truck driver all he can. This is the video from the dash cam of the state troopers, the police in the New York State, not too far from my home. And you can see the driver, he can see the bridge coming, and he thinks he will make it, and he does not listen to the police driver. And he goes and hits the bridge and gets stuck under the bridge. Not much damage to the bridge, but of course the truck got completely damaged. The traffic was backed up heavily in this lane, in this bridge for several hours. So this is something which very regularly happens when you have these kind of impacts. This is an example for agricultural hoe. You know, the driver forgot to secure the hoe properly. And you can see the impact, the amount of impact that it could cut the deck right from one end to another end. So if you really have to cut the deck, this is a good technique. You know, you can just chop the deck from one end to another end. You can imagine the amount of force and effort you will need if you want to really cut the deck. You can see from the top that, you know, how far it started from one end, almost cut the deck to the other end. This is one which was, you know, in one of the terrorist bombing where you know, they knew actually exactly how to collapse the bridge, you know, just destroy the pier, the bridge will come down. On the right hand side, the slide that you see, this is a vehicular impact when the truck hit the bridge pier and, you know, the bridge collapsed. That's another example where the, you know, truck hit a bridge pier and the bridge collapsed. This is Nebraska in 2003. Another example where the truck actually hit, the tanker trucker hit the bridge pier. You can see one of the pier is gone, the trucker is gone. Unfortunately, I don't think the driver survived, but the bridge was intact. The bridge did not collapse. It has enough redundancy in terms of continuous girders and other things that it could survive. This was in Texas on May 14, 2014. This is another example with the, you know, the fire, the truck burned down. You can see this pier completely damaged, but apparently the bridge has enough, you know, alternate load path and capacity that it didn't actually collapse. Another example, you have a 2-pier bend. So, you know, sometimes we think 3-pier bend is good, but just 2-pier bend. You can see almost a very little axle load carrying capacity for the bend now. The pier is almost gone. You can see the bend is kind of like bending here, but still the bridge survived. There's another example. This was a multi-span simply supported bridge. You know, the pier went down, you know, the bridge came down. Another example in Texas, you know, a lot of these incidents are in Texas where you have a speed high, the roads are, you know, isolated. So you can see another example, the truck hit, you know, the bridge completely went down. To study the vehicular impact, there was a test done at TTI in 2010, and the idea was to find the type of impact force that might come. You know, this truck was actually, you know, tractor semi-trailer truck, but the pier was actually completely rigid, made of steel. And the idea was to find exactly what was the level of force that the bridge pier should be designed for. And you can see the two type of impacts. First, the bumper impact, you know, bumper hits the bridge pier, and then once the bumper is done, the trailer comes, you know, 80,000 pounds of the force of the trailer. The speed is low, but trailer comes and, you know, it squeezes the bumper, the engine between the pier and the trailer. 80,000 pounds, moving very slowly, but really squeezing. And, you know, applying massive amount of kind of like pseudo-static force on the bridge pier. Based on the testing, they found some data, they applied some filter, and they came out that, okay, you can design the bridge pier for 600 kips. But this 600 kips is, you know, completely blind in terms of, does not consider the speed of the truck or weight of the truck or any other factor. It just says blindly designed for 600 kips applied at 5 feet height. In reality, you know that, you know, if you have a very heavy truck versus a light truck, you have a high speed versus a low speed, the level of damage will be low. If a roadway has 40 miles per hour speed, then there's no reason to design that roadway for 70 miles per hour impact. That will be uneconomical design. So with that in mind, we Federal Highway invited us to work on this problem. I think this was in way back in 2014. But before that, in 2012, my first PhD student did the PhD on this medium weight truck. Unfortunately, his work actually we never published because I had some doubts about simulation and how accurate was the simulation. There was no clear-cut calibration, so I held on to his thesis and said, well, publish in the future. So our initial work in 2012 was actually for medium weight truck, but then starting 2014, we started working on heavyweight truck. This is a model of the truck that you saw earlier in the video that at the TTI. It's exactly the same truck. When you have a vehicular impact, you have several on the bridge piers. You have several damage modes. You have the pier eroding. You have the shear at the footing, heavy on shear. You have a rebar severance. You can see in this figure that some of the, there's a severe damage. Breaking of the pier might just break somewhere. Spalling of the pier and the plastic hinge formation. Out of that, the primary mode of failure is actually shear failure, the most dominant mode during the accident. This massive amount of shear, the bridge just fails into shear. If the bridge piers are not designed appropriately for the shear, then it will not survive. We did all the work in LS-DYNA. In LS-DYNA, material model is important. We use two material models for concrete. We use MAT 159 continuous cap surface model. This is a damage model where you can simulate the deformation and failure of the concrete. This was developed specifically for this impact problem. And for the steel, we use MAT 3, which is a kinematic plastic kinematic model, which is widely used to simulate isotropic and kinematic hardening plasticity into steel. It considers again rate effects. This model also, cap model also considers loading rate effect. So these are the two models we use. We have a lot of calibration for these two models, which I'm skipping for the interest of time. But I want to show you one large scale testing that we did 2 years at the Federal Highway Outdoor Laboratory in Washington, DC. It's called FOIL. Here, this large pendulum system where we built this, three pier bent system. And the idea was one is weak, one is strong, and we come and impact the pendulum. This is a 2-ton pendulum. We impact the pendulum to the pier, and then see the response. And then actually, the idea is to take this to LS-DYNA and calibrate and see our test and simulation how well they match. There's a paper in Engineering Structures that was published recently. It discusses in detail about this work. So, sorry, this slide. Okay, so here, this is the largest scale testing and simulation. This is the design impactor. So before designing the impactor, actually, we took this single unit truck and impacted on the same frame. And you can see here, the solid line is a pendulum impact and the dotted line is a truck impact. Our idea was also to be able to simulate some kind of truck impact. So we matched the peak, the most dominant peak to the pendulum impact. And also you have honeycombs in the pendulum. The honeycombs actually can simulate kind of like a multi-peak behavior of the pendulum, or of the truck impact, like the engine part. When the engine part hits, this is softer material and it can simulate different peaks. So, but our goal was to match this truck impact. You see red line, and this is a pendulum impact, solid line. So some kind of dynamic behavior to be able to simulate in the simulation. So this is the testing setup. We put the testing here on this one, anchor everything. We also had a lot of strain gauges. We had high-speed camera. I'm not showing the result for the strain gauges because some of the strain gauges in the impact area broke, and some strain gauges we got very good results. So those are in the journal paper. But we had a lot of high-speed camera where we could actually capture the deformation profile exactly. So this is the setup of the field test. When this comes and hits the bridge pier, that is the pier bend system, and this was the test, more than $70,000 test, 2 years of work for 30 seconds of pleasure. But we learned a lot from this one. We took this model back to LS-DYNA. We built the model in Alexandra, the impactor, exactly the same way. And we did, this is the impactor where you have these are the honeycombs units. This is the nodes. You have the steel mass block. This is a point A. We monitor the acceleration. Concrete block. This is the impactor that has been used for many testing. First of all, we'll look at the honeycomb behavior. This is the actual, in the bottom that you see, this is the actual honeycomb behavior after crushing. So you can see how the honeycomb crushed, and in our simulation, how the honeycomb crushed. They're almost a similar, behavior of crushing of the honeycomb. So that shows that we are, our model is good. This is the test, the force. We monitor the force by the accelerometer. So the dotted line is finite element. Test is this one. In test, there is slightly higher level of acceleration compared to simulation, which is understandable because of cable tension and everything else we might get, but we are not exactly modeling the pendulum as it's hanging, impactor. But if you look at the velocity of the acceleration point A, then it matches relatively well. And if you look at the various points on the model test versus finite element, we actually get very good matching. So displacement time history is matching very well. We get it from the high-speed camera, so that's a very good confidence that what we are doing in the finite element and what we are doing in the test is a very good representation. So let's come back to the simulation. This is the truck that was used in TTI. And, this is finite element model was built by Batal to Federal Highway sponsorship. And after they built the finite element model, we took over in 2014 for the vehicular impact. So we look at this test from TTI. You have the bumper impact here in the actual truck, and this is our simulation of the bumper impact. This is the trailer impact, means once the bumper hits and trailer comes crashing and crashes the engine between the pier and the trailer. This is the case, and this is in our case. You can see the sand. The trailer was full of sandbags and sandbags popping out all over the place. You can see here the trailer is basically broken to pieces. Again, we use the semi-rigid cargo, which simulates the sandbag. And if there were sandbag actual, they would have popped out from here. But the damage behavior, tire damage, everything is almost the similar way. Then we look at the force time history. And the force time history, if you look at, this is the total force on the column, on the pier that you saw. And you can see with the actual test from TTI, 830 kips force coming here. And from our simulation, we have 928 kips force coming here. So they are pretty close for the engine impact. So after engine impact, there's a bumper trailer impact when the trailer comes squeezing. And for that, actually, test gives us around 528 kips, and we are getting around 432 kips. Given that we have the sandbags, which is semi-rigid cargo, but not exactly the way it is, because a lot of sandbags burst, and the peak force representation, we consider complexity of the testing. That is a very good, modeling. So very good representation of the actual truck behavior. So we go with the truck model. We take the truck. The next is the modeling approach. We are actually going back to what we did in 2012 to simplify our model. So in 2012, actually, we did work using the full bridge model. This is a 3-span bridge. We have a single unit truck. Problem is, when we do simulation with this kind of model, the model is so big that one simulation takes around 12 or 13 days. Now we had to do, for our research, we had to do thousands of simulations. So doing this was really not possible. So we went from this bridge, we went to the pier bent model. We were 3 pier bent, and if you consider this pier, half of the mass here, half of the mass here we put on the top, and we do the pier bent model. And which is the whole bridge and pier bent model, they match very well because the effect is localized on the pier. But this model also takes us several days of simulation if we have to do in Alexandra. So we go next and we look at, we start modeling that, okay, we have a pier bend model, but can we do further? You have a pier bend, piers with fixed top, pier with fixed top and bottom. And when we start comparing, we find that piers with fixed top at the top and bottom is actually sufficient because if you look at here, at this point, the piers actually behave like for this localized impact, they do behave like they are fixed. At the bottom also with the foundation encasement, they do behave like fixed. So pier in this impact zone, they do behave like fixed peaks, and you can see the time history. The zone up to what matters is you go from here to here, and this is the point where there's a significant damage. So up to this point, we are interested. We are not interested in this zone, but up to this zone, it's pretty good. You can see the impact force time history also. This matches very well. So we come to this model, and this model actually takes us 4 or 5 hours to do one simulation, which is practically feasible. So we take this, our heavy truck model with the fixed pier, and we take this different kind of piers, 24 inch to 42 inch, 30 rectangular, and 30 inch to 42 inch in circular pier. These are the most commonly built piers. And then we do the single unit track, multiple unit track time history. So let me show you the typical time history. When we do vehicular impact, this was just a representation of time history, how a pulse may look. If you have a triangular pulse like this, so we could actually make it like a triangular pulse, just a representation. But if you look at a typical the heavy unit truck, this is how the typical time history works. It looks like. So the first peak that you see, this is the one when the bumper hits the bridge pier. And then it goes to the second peak. This is when the engine comes in contact with the bridge pier. And once the engine comes in contact, the engine will apply heavy force, and then, engine gets deformed, the force comes down, and then slowly, this is the squeezing effect of the trailer. It goes, and then it comes down here. So this whole portion is the squeezing effect of the trailer on the pier. So you have the bumper impact, engine impact, and the squeezing effect. What we can do is, if you want to develop an analytical model, this time history, we can say, okay, I have one triangular pulse here, I have another triangular pulse here, and this entire area that you see here, we call another triangular pulse here. So we can say our impact force time history is like this: one pulse, second pulse, third pulse. So once we have this pulse, then we need to find out F1, F2, F3, F4, F5, and T1 to all these parameters. What we do is also we need to find out where exactly to apply this force. On the bridge pier, right? You have a bridge pier. Where do you apply the force? Here, here, here. Where do you apply exactly? Right now, the ASTO gives you 5 feet high, but this is the dynamic force. Where do you exactly apply? So what we do is we do a lot of simulation, and from the simulation, we plot this contour of height versus time, the pier height versus time, and look at for different velocity and all this thing, that how is the impact force distributed. And we see this dark area. This is the bumper impact, the first contact. This is the engine impact area. And this is this height, that range that you see. This is the trailer impact, because once the trailer hits the bridge pier, say once the engine is crushed, the trailer will, because of the speed, will tend to kind of like topple, overturn, tend to apply the force at the lower end of the pier, in the lower portion of the pier. So this is the trailer height. So based on this, we define 3 zones. This is the zone 1 of the pulse for the, this is the impact zone 1, which is your bumper impact. You have the impact zone 2, and they have the impact zone 3 for the trailer impact. So we define these 3 impact zones, and then just to see how good is our impact zone. So we take this time history. Instead of truck impact, we take this time history, apply this time history into the 3 zones that I have, these 3 zones, and compare that with the actual truck simulation. This is the truck simulation. This is just the pulse time history that we apply to our model. I can see how good they are. Up to this point, is almost exactly matching. So that shows that, okay, the height, the forces we are applying is actually good representation of actual truck model. And then to find the parameter of these peak forces, F1, F2, F3, F4, we do a lot of this simulation, almost 100 cases of parametric simulation for different weight, height combination, and then we try to find for different weights and height, we have these plots, F1, F2, F3, F4, 5, T1, T2, T3, T45 as a function of velocity, then function of pier size, then function of weights. And once we are done with all these things, then we go into the complex the regression analysis to find the equation for F1, F2, F3, F4, F5. These are the peak forces in the pulse. For example, if you look at the F1, that's the bumper impact. That's a function of velocity only, because the trailer weight really doesn't come into the picture. If you go to engine impact, we assume that our most of the weight is considered into the trailer. Engine weight is really much smaller than compared to the trailer weight. So you can say again, it's mostly function of velocity. F3 is again function of velocity, but when we go to F5, which is the trailer weight here, this one, it is function of the weight of the truck. So that makes sense based on what our physical understanding is. Again, we find the T1, T2, T3, T4, 5, they are different parameters. Once we have this model, then we compare impact force from our equation versus the actual impact force. And we say that generally they are in pretty good close range of what we'll get from the actual truck simulation. The FEM is a finite element model, T, this is the equation. In the range of domain of design that we want to do, this kind of variation may be acceptable given the complex phenomena that we have here. So also we start looking at comparing now, this is the track versus pulse, this is the triangular pulse. So you can see the damage modes in 3 cases. This is 60 mile per hour, 50 mile per hour, 60 mile per hour, 30-ton track, 20-ton track, 30-ton track. So they are different combination. You can see the force time history. The important part where the peak impact force goes, the displacement, you can see this is scale is in inches. This impact the displacement can have in several inches. So you can see the matching is really outstanding. Even in this case, actually, you have to see this is going to collapse. And here you can see that matching is pretty good in this range. And beyond this, actually, they just diverge. We can extend this approach to the circular P also by just taking 45-degree exposure area. That's the area which will come in contact with the truck. So we can distribute the load in this area and then apply the same model that we have. This same model we can apply, but by considering the distribution of the load in the 45-degree angle area. Again, for the circular pier, you can see the damage mode. So particularly if you want to see at the high velocity, 70 miles per hour, the damage behavior almost looks similar. But if you look at the truck simulation versus pulse simulation, the trucks, there's a big difference. But what we are really interested in our design mode is here up to this point. Beyond this point, the pulse here, actually the pier gets damaged because the pulse is more conservative, it's more heavier demand. It gets damaged, and you can see this completely separating. In design, we are not going there. In design domain, we are probably going to stay up to this point. So again, you can see all these cases, the matching is pretty good. So once we are done with that, then we come to the point of doing what we call is the performance-based design, that we want to design the bridge pier. If you look at the earthquake engineering, then we want to design for immediate occupancy, we design for collapse prevention. In earthquake engineering, what we do is we do the capacity design. In the capacity design, if you take a simple example, you have a fixed column, you apply force here, L/4, TL/4, will force it to go to the plastic hinge formation. And based on this plastic hinge formation, we'll be able to find that 8 MPa/L shear force. The foundation on this part, the part of the pier should be designed for 8 MPa/L shear demand. So if we know this impact force and we design that for 8 MPa/L, then probably we should be able to protect for the capacity. And that we should be able to prevent the shear failure of the bridge, which is the dominant mode of failure. So you can see some example here. The bridge has a shear failure, right? And this one, it doesn't have shear failure. There's a hinge formation. This is what we want in our design, that we want to make sure that the point of impact, you have the hinge formation. So we want to illustrate the effect of capacity design. So this is the non-capacity design pier. This is the capacity design pier. You can see the difference. Of course, there's some more finer detail here that you have a more confinement, slightly different detailing, but not significant difference in the rebar detailing. Size is the same, everything is the same. And if you look at the plot here, this is the height of the pier. And on this, we plot actually the shear deformation and plastic rotation. So SD is the plastic deformation. This is the non-capacity design pier, and maximum plastic deformation is up to this point. But if you same pier, if you do the capacity design, you can reduce the plastic deformation at this point. Similarly, the pier rotation, non-capacity design is this one. With the capacity design, we want to increase the plastic rotation slightly more. So reduce the shear deformation, increase the plastic rotation, let the pier form the hinge so that it will not collapse. That's the design philosophy they want to follow. So based on that, if you look at the framework, you have the minor damage, you have some plastic hinging, moderate damage, and we want to have shear damage, but still prevent the collapse of the bridge. So what we do is we go into a lot of simulation, more than 100 simulation, observe the damage and convert the damage in terms of shear deformation or plastic rotation. All right. On the x-axis, what we plot is D1, D2. D1, D2 is, if you remember that pulse we had, we had this triangular pulse. And for that triangular pulse, when we had this, when we plotted this triangular pulse, so demand for this one, that's D1, D2, and the demand for this pulse will be D3. So what our design approach is that we take the D1, D2, max of D1, D2 divided by the capacity of the bridge pier and plot it. And you can see very nicely that you have a zones. This is the minor damage zone. This is the moderate damage zone. This is a severe damage zone. And then, but when the engine impact comes, D2 is engine impact. After the engine impact, pier gets damaged. Concrete is cracked. Concrete is no longer useful. Then what comes is the rebar detailing, which plays the role. So we look at the D3. And when we look at the D3, we just look at the shear capacity of the rebar case, not the concrete. And again, you can see we have very minor, very nice 3 zones of damages. And on that basis, we can go ahead and formulate our design guideline that, if you are here, then design for minor, if you are design for minor damage, take this and take this. Design for moderate damage, take this, take this. Severe damage, collapse prevention, stay somewhere around here. So we have this design guideline that you can find in the paper. And if you follow this design guideline, then we can design this pier. And then what we did was after this design guideline, we took these cases were not part of original simulation. So we take higher loads and different speeds. This is the column heights, the different column heights we took. And we did this predicted damage based on this chart. What is the predicted damage? And then we go on to look at the actual damage through the actual truck simulation. And we can see that our damage levels match precisely where they are. So that gives us very good confidence that our model is very good, the approach is very good, can be used in the design. The beauty of the whole thing is that you can actually do this design in any design office, because all you have to do is take any commercial software like SAP 2000, build the fixed model, the bridge pier, apply the time history triangular pulse, get D1, D2, D3 using the dynamic analysis, and then just go on to do the pier design. So whole design can be done in an hour. How good is the design? Let's take the case for the comparison. We look at the ASTO 600 kips versus actual impact. For ASTO, you design a bridge pier for 600 kips. You have 30 miles per hour, this is the damage. 50 miles per hour, this is the damage. 70 miles per hour, the pier is mostly gone. You have the plastic hinge formation. I'm pretty sure if you let it run on the LS-DYNA for longer time, we'll see this pier collapsing. But same bridge pier, if we go with our approach, all right, this is the ASTO 70 miles per hour ASTO design, and this is our performance design. See the pier impact, no plastic hinge formation. What exactly is the difference? Well, longitudinal rebar is the same. Everything is the same. The difference, the stirrup, the confinement. The ASTO required number 6 at 12 inches spacing. We are saying number 6 at 6 inches spacing. Such a minor difference in the stirrups, which will not be even a very small fraction of the cost of the material, that you can achieve this performance. So that says that, okay, if you follow this kind of approach, you'll be able to protect the pier even at the speed of 70 miles per hour. And it gives you, if you look at the charts, you can actually predict where you want to be, where you want to design, and where you want to stay. So that's the part of our performance design that we worked on. The next slide, I want to talk briefly. I have a few more slides on overhead impact on bridges. So slide went a little bit. So I'm pretty sure you guys remember the Skagit River Bridge. So I'm starting from there. The Skagit River Bridge, the bridge, I think in 2013, the bridge collapsed. This is the Skagit River Bridge in Washington State. This truck came with this oversized combination vehicle, the trailer, this is semi-rigid trailer. The trailer came and hit the bridge at this point. When they hit the bridge at this point, the bridge, one span of the bridge collapsed in the river. So let me show you. This is the span of the bridge collapsed in the river. There were number of vehicles and the people fell in the river, I think around in the range of 10 or so. But fortunately, nobody died. Everybody was rescued, but the bridge span was damaged and the bridge had to be replaced later on. We used again our similar, tracking model that I showed you already, and we go and build the model in LS-DYNA. We had to go in a little bit iteration in terms of rigidity of the track model. That we didn't have test data, but we're trying to figure out how rigid is the model. If the trailer is very rigid, it will cause a lot of damage, but the truck will not get damaged. If it is not rigid, it will just the truck will get damaged, no damage to the bridge. It was somewhere in between. We wanted to replicate this level of damage to the truck as well as the collapse of the bridge. We wanted to do both. So it went through several iterations because there was no data available on the truck behavior. So you can see this impact process. This is the impact with the truck. Truck is impacted. A few seconds later, this is the zone of impact in the truck. This is the damage on the trailer. I can see this corner damage in the trailer is pretty much similar to this corner damage in the trailer here. The zone of impact matches very well. And then we go on to look at the damage mode in the simulation. So this is in the bottom that you actually see, this is the actual collapse. You have one hinge here, one hinge here, one hinge here. And this is the same as, 3 hinge formation. A detailed paper on this actually currently under review in the engineering structures. I think it should be published fairly soon. If you look at the force in the member, when the truck hit this member here, right here, this member that you see, this lateral brace member, the force in that member was actually close to 400 kPa. Now, those members are not designed for lateral force like this 400 kPa. And that's the reason, the bridge, that member basically, and the reason the bridge collapsed was because it was simply supported. So the entire span was actually dragged off the support into the river. There's another type of research that application that people have been doing, and this is one example that we saw is you put a box beam and the entrance in front of the bridge pier as a fascia gutter, or at the entrance of the tunnel, so overhead trucks cannot enter the bridge area. And this is how it looks like. You have this box beam which is in the front of the bridge, and the truck comes and hit the bridge. And we took this example for actual application where the truck goes and hit the bridge. And if you look at this process, so it will go and hit the bridge, and after it hits the bridge, at this point at 2 feet deformation, it will get completely damaged, this example bridge. And then we went on to modify this original girder has 2-inch plate. We went on to modify 4-inch plate. If you look at the 4-inch plate, we can change the beam design for 40 mph rigid cargo impact to the point where it will serve its purpose. It will not get completely damaged. It will prevent the truck from entering the bridge or tunnel. But after the impact, if it is severely damaged, then it may have to be replaced. Again, if you look at the peak force in this case, it's a rigid cargo, only 40 mph speed. You have 2600 peak force. So the idea of talking about these numbers is to give you a feel about what is the range of forces that are involved in this kind of impact, that the magnitude of force is simply too high. So one approach is, of course, design these members to be strong enough, but the other is to design the redundancy so that if there's impact, then bridge doesn't collapse and you can repair those members. We also look at some parametric model of how you could design a model for the steel box beam, for this box beam. We did this by the simulation, but you can't do this complex simulation all the time. So what do? Well, we go and do the parametric study, and then we realize that the force acting here on the box beam is actually a triangular pulse. All these are different speeds and weights. They're all triangular pulses. So what we do is we assume it is a triangular pulse. Based on the simulation, we can find this F, 0.12 V is a function of velocity and weight. So by simulation, we can find this TD also. So if you look at the basic structural dynamics, we do this kind of triangular pulse. It is exactly the same triangular pulse. You apply this triangular pulse on the girder for a 2400 millimeter loading area. And if you do the simulation, you can see the pulse loading versus truck impact. They match very nicely enough that we can use this model next time to design this production beam. Again, this is a simulation versus impact. They are within 15% plus minus, 20% plus minus, which is good enough given that kind of complex situation we have. We also look at a lot of this damage to concrete girders, which are the impacted and damaged. This is one example for pre-stressed concrete girder where the truck goes and hits the bridge. You can see this actual impact here. This the girder is damaged. You can see this girder damage. And from our simulation, you can see the line of damage that we are matching, on this girder, that we have this W-shaped yellow line. And you can see this how the girder is getting damaged. Our simulation result, again, this was for the semi-rigid trailer. But if you look at the soft trailer, then there are scratches, and you can see so there's some minor scraps here. And same thing we see in our simulation, there's some minor scraps on the girder. The same thing comes in our simulation. So again, we are able to match very nicely. Sometimes people do fiber wrapping on the girders. So to see the impact, we ask by federal highway, how good is the fiber wrapping? We say, okay, let's simulate fiber wrapping. So we take this girder, we put the carbon fiber wrap here, and then after that we do the simulation. This is the damaged fiber wrap girder. This is our damage here. You can see the diagonal crackings in this zone. So, and if you look at CFRP rupture in this zone, that's where the CFRP rupture is there. So we are able to match again with what really happened in the field. And if you look at the effectiveness of CFRP is this is without CFRP, and if you increase the thickness of CFRP, there's a certain point, but you cannot completely eliminate the damage. There will be permanent deformation to the girder. You can reduce from almost like a 14 inch, 13 inch something to half of that, around 6.5 inch, but still the girder will be damaged significantly. Like you can see here that the girder has been damaged significantly, and you have to either rewrap or do something or replace the girder. So that's our fiber wrapping. But we also have been looking at, you can see again the effectiveness of fiber wrapping. It works, but it doesn't really work completely. And then we are looking at another measure. We are designing a protection device. It's a part of honeycomb, but the other components, and it's a part of patent that our patent is pending for this impact protection device. And for here, actually, I'm just showing the very quick result that this was a CFRP production, where you can see that no matter how much you did, this is with the weight of the truck. That as the weight of the truck increases, you can say your damage will be 180 millimeter, the maximum permanent displacement. And when we have a honeycomb, we can literally completely prevent the damage to the girder. Idea is in our device that when the truck comes, honeycomb with some other supplemental component, is able to take the shock, and dissipate quickly in terms of damage to the honeycomb, damage to the compressed air, which is released to the air. So we take all the shock off from the impact and prevent any damage. And also our mechanism prevents any transfer of the forces to the actual girder in a significant way. So you can see that honeycomb works very well. In fact, next week or later this week, or maybe next week, we are doing a large scale testing on this honeycomb, to see the effectiveness. And we if we get the same result like we are getting in the simulation, then we'll go to the next phase where we'll do testing on the large scale base with the actual truck impact. And that works out, then we'll have an effective solution to prevent damage to bridges, overheight, bridge girders, which is again very significant amount of bridges that almost every state of the country that bridges are impacted. And we'll be able to, the DOTs will have Department of Transportation officials will have this option to install this device to prevent any significant damage to the girders. And if this device is damaged, then all you have to do is go to the site, take the wrench, take the device out, put a new device, which will not be very expensive. Take a new device in place, and your bridge is ready for performance again. So that's, I think, the last slide that I have. So a lot of things in our presentation, but the key part is the performance-based framework for design of bridge piers against vehicular impact has been developed using calibrated models for piers and tractor, similar to tractor, based on truck test data. 3 triangular pulse models we have developed, and we have shown that this model works very well. We have proposed a performance approach, and so that this model works. We have also done a lot of simulation on LSNM to predict overall impact on bridge girders and design measures. Something that I didn't get the chance, and probably will talk in the future, that we have done a lot of work on the barriers, roadside barriers, the bridge railings, concrete railings, steel railings, subjected to truck impact, where we have developed the similar kind of demand models, that if you use those demand models, then you don't have to do the testing. Those models could come close to actual the testing. So you can use the demand models to design those barriers. Currently, ASTO gives you just one static force, one number. That is not good enough. In fact, it could be misleading because the actual loading is dynamic. Our model is a dynamic model. The approach is a dynamic, performance-based approach is dynamic. And based on that, if you use and here we have several papers on the barrier that are under publication, you can look at them. And those models give you very good capability to design the barriers also. So our work covers overall bridge piers, overheight, girders, overheight structures, and then also the barriers, which are side impact. So last 5-6 years, we have massive research activity in all aspects of impact for the bridges. And I really want to thank you for inviting me. It has been an honor to give this keynote speech. And, and I'm hoping that we'll have a chance in future to talk about further work that we are doing. In fact, we are sure to go and do this full-scale testing at one of the crash testing facilities, which will be really exciting to share with you that how this some of the work we have done and how its verification works through the actual crash testing. So with that, I will stop talking. I think I have been talking, I've talked a lot, and I would really love to have questions from you.
Thank you, Anil. Yes, there is one question that I can read from the system. It came from Elena, and her question is, could you comment on the maximum response of the bridge and the impacted pier under the application of the impulse force, the track collision? The maximum bridge response would occur in phase 1 when the loading is still applied, or in phase 2 under the free vibration.
Well, so it's like this. Let me go back to the, under the pier impact. Let me show you the time history, and that you will know what exactly is happening. So if you look at this as a good example, that you have this truck simulation, and you can see, you have this goes, and this is the bumper impact, the bumper impact, and the bumper impact, the force starts in, the displacement starts increasing. So this is the point of contact where the bumper touches the bridge pier. and it goes to the engine impact, and engine impact doesn't do much. And then as the trailer, right? If you look at our pulse model, so you have the bumper, you have the engine, and after the engine, this trailer. This is the massive force. This is the squeezing force, 80,000 pound truck weight. Imagine you're applying 80,000 pound static force on the bridge pier. It's not pre-vibration. It's a static force which goes and applies and keeps on increasing for up to 0.8 seconds. So if I come back to my chart here, it goes and it goes to this point where you have this goes here, and then from this point on it goes in the free vibration. So the major amount of displacement, major damage will actually occur when you have this when you have this this squeezing force. This is so what may happen is if your speed is very high, under the engine impact, the pier may get cracked, completely damaged. Pier may collapse depending on the speed and weight, but if pier has not collapsed, this part will come, and this part will finish the story. It will cause the collapse of the bridge pier. So I hope that answered your question. If you look at some time history, I think I have some further time history later on. So, in terms of relative magnitude, you can see actually that we start from very small displacement, come to the engine impact 0.06, and at the highest level is go to 0.14 inch, displacement, depending on the speed. This is 60 mile per hour, but when it 30-ton truck, but this is 50 mile per hour, 20-ton truck, different kind of pier, 1.4 inch. In this case, actually, it's higher because the pier is completely damaged. You can see much higher, kind of like a plastic hinge formation occurring. Your displacement might actually go at this point of 3 or 4 inches in this range. So it really depends on the speed where you are, but the damage can be much higher level. And again, our if you look at our pulse model, we say our pulse model is up to 0.8 inch, right? This goes up to 0.8 inch. But in our actual simulation, when we do the simulation in the LS-DYNA, we don't go up to 0.8 inch because we see that the squeezing force is applied, but at this point, there's a permanent deformation of the bridge pier, and the speed has gone down. So we do simulation up to some point, and then we stop because LS-DYNA takes a lot of time for the simulation. So to minimize our computational cost, we cut the simulation at some point when we see this results are stable enough. But in this case, you can see that we went all the way to up to 0.8 inch of simulation, and this is the actual track, and this is the pulse loading. And at some point, they will converge. So up to 0.8 inch is still under forced vibration. So we never went into the phase of free vibration because that's not important. What we are looking at is the bridge going to collapse. This is a quasi-static zone of the loading where the squeezing force of the trailer is coming, and that zone itself is very significant that it can cause the collapse of the bridge pier.
Thank you, Anil, for this answer, and hopefully we will have you face-to-face in 2022 in Istanbul for the next conference, and you can talk about your future research. That I see that you will be doing some more of impact, and
yes, and the presentation before me by Dr. Hussain, it's very interesting on the suspension bridge.
Yes.
Last couple of years, we have been working on the redundancy of suspension bridges, where the cable tied bridge, where we have one of the suspension bridge. We have very, very complex model of the suspension bridge, where we are looking at different failure modes in the event of loss of critical components like suspenders and other members. And our model is very reliable because we have spent a lot of effort in looking at every aspect. So if we get time, actually, because you have the repair part, and we'll look at it, and we can show what kind of behavior this kind of longest time cable stayed bridge tie-downs bridge and suspension bridges have in the event of sudden loss of member corrosion and all these things. So probably that could also be a very interesting topic. Our report is about to come, by end of this year. So by the time, probably you'll have access to the Federal report on that, redundancy of long span cable supported bridges.
Oh, thank you, Anil, for this very nice presentation, and it was really nice having you in the conference.
So this is the recorder, right? So maybe hopefully you can, I can have a copy later on.
Oh yes, definitely. Yes, we will make a channel for this, and you can watch from the YouTube channel.
Okay.
We are in the process. Like in the next weeks, we will have it.
Okay. All right. Great. Thank you very much, and thank you for inviting. It was a real honor to talk to you all and some of the colleagues that I could say, Khalid and Rob and others. It was nice seeing you guys, and thank you very much.
Thank you. And now Polat Gülkan will be our next keynote. Polat Gülkan is a very famous engineer in Turkey and academician as well, and he's worldwide known in seismic area and earthquake. And he's the former president of the Turkish Association for Bridge and Structural Engineering. And so the floor is all yours, Polat Hocam.
It seems that Professor Agrawal is still sharing the screen, and I cannot share mine.
All right, John will handle that. Yes? Huh? Okay, now you can take the control.
I answered. Sorry about that.
Okay. Do you get to see my slide?
Not yet, but John will do something. Yes. Right now. Huh?
He needs to share his screen.
Okay, you can start sharing your screen, Polat Hocam.
Yes, but Zoom does not seem to be willing to give me that opportunity.
It is at the bottom. Can you see that share screen button?
Well, let me do this.
Okay. Well,
Is that better?
yes, I think. Can you see at the bottom the share screen, the green button?
No.
No. What do you see? Like just QA?
I see my own screen, and
if you move your mouse to the down, you will see a band. It is a hidden one. When you come close, it just appears.
I know I use this almost on a daily basis, except that this time it doesn't seem to work.
John is with me, so he will try. What can we do, John?
No, I'll make it happen.
We can make host.
Host yaparsa kapatırsa kapanır.
Okay.
Is that better?
Perfect. You can see your screen right now.
Okay, and let me go to the presentation modality of this. Ladies and gentlemen, the way I see it here, only the few dedicated and hardcore participants have remained, but it still is a pleasure for me to be able to address you this evening on the occasion of the closing session for the 4th Istanbul Bridge Conference. I am truly honored by this. Several references have been made to performance-based engineering, performance-based earthquake engineering during the course of the discussions of this conference. And I would like to now cast a somewhat detailed and critical look at this emerging technology. This is not meant to be a denial of the significant intellectual investment that has been made in bringing the performance-based engineering and earthquake engineering to where it is right now. It is simply a lighthearted attempt at looking at some of the work that still needs to be done before we can use the method with any degree of confidence. Because of the persisting global pandemic brought about 9 months ago, we have had to switch to this remote way of meeting on the internet, but we are hopeful that next year, when things are better in the health field, we will be able to have a real conference on our hands. Now, I would like to make a statement right at the beginning that summarizes this particular presentation. Now, performance-based earthquake engineering, or performance-based engineering, as we have repeatedly seen, makes increasing use of statistics. Now, mathematics and statistics are fine, and they have actually brought technology and engineering to where it is right now. But when it comes to understanding the secrets of nature, particularly as it relates to the revelation of the processes that lead to the occurrence and propagation of the effects of earthquakes, statistics may seem to be the only tool to which we can resort at the moment. However, unless we make use of the more fundamental laws of nature, I think that the error margin represented by the standard deviation will not diminish in the near future. And therefore, there will always be a margin for error, and therefore we should be sober enough and modest enough to admit that the statements in relation to the 475-year return period earthquake or the effects and damages that it causes are bound to be shrouded in a lot of uncertainty and possible future errors. Therefore, statistics is fine, but it's not sufficient and it needs to be perfected. Now, the derivation, the motivation for this presentation derives from the age-old problem. We build, we design, and analyze structural systems, which sometimes are subjected to earthquake ground motions, and occasionally to strong and very strong earthquake ground motions. Now, the engineer's duty, of course, is to make sure that the safety of the occupants is guaranteed through non-collapse, that the safety of the public is protected by the designs that we submit to the community at large. Now, are we endowed with enough confidence to make sure that the safety of the public, the safety of the built environment is guaranteed by our design. Well, each earthquake teaches something new, which is, of course, the way in which science and technology have developed until now. And we should not shy away from making admissions at times when it is called for, that we learn from our past mistakes, we learn from the lessons that earthquakes teach us, and therefore we can only perfect our tools by making use of the lessons that we have learned from nature. Now, I will consider in particular tonight the case of 3 identical buildings that have been subjected to very strong ground motions on 3 different dates. Now, it is very, very rare indeed that a given building should be subjected to strong ground motions twice during its service lifetime. Identical buildings sometimes experience the same ground motion, granted, but that is the same ground motion, not the same building experiencing 3 different strong ground motions. Well, this has happened in a sort of a roundabout way in Turkey during the course of the last 30 years or so. And I think that there are lessons for all of us to derive from this experience. This is what I propose to pass on to you tonight. All of them deal with the performance of these identical buildings. Now, on a lighter note, perhaps we should remember the experience and the teachings of a gentleman, probably a mythical person named Procrustes. The fame or the infame, if there's such a word in the English language, derives from the fact that he was a stickler for precision and exactness. Now, he would offer tired travelers in ancient Greece who would be traveling from one city to another city on foot. And of course, the travelers would be tired by the time night fell, and Procrustes would offer them his bed, which of course the travelers would be only happy and grateful to accept. However, there was one condition on the offer that Procrustes made. The person, the traveler, needed to fit the bed exactly, not a centimeter longer and not a centimeter shorter than the length of the bed. When the traveler failed this exacting test, he might well lose his life. Therefore, the Procrustean estimates are sometimes taken to mean estimates that are made with hindsight and not necessarily foresight. Another name, and his advice should be handy at this time. Feynman once said that regardless of perfect seeming your theory might seem, unless it passes the exacting experience of observation and experimentation, the theory cannot be declared to be correct. Therefore, nature, in the case of earthquakes, places that. Now, there have been many, many round table or round robin experiments made to perfect the methodologies and tools that we have developed over the course of the structural engineering during the last 50 years. Tests are run and teams are invited to predict the outcome of the tests. And that is truly a challenge in spite of the perfection that we think we have reached in terms of the analytical and computational tools that are available to us. Sometimes the predictions made on the basis of the givens to us fail to duplicate the experiments. And of course, we should learn all from the reasons of this divergence. This is a cartoon that depicts how a royal person, possibly a king, proves himself to be a perfect shot. Now, one possible exception to a single building experiencing multiple storm ground motions is the hotel building in Van Nuys in California. However, this building does not quite represent the experience that I'm about to relate to you. The building was retrofitted after the 1971 San Fernando earthquake. It was subjected to a strong ground motion in 1994 during the Northridge earthquake. But the building had been retrofitted, and therefore it was not the same building, not the same structural system. And a lot has been learned from the experience of the Van Nuys. Now, here's the geographical location of the buildings, which over the course of the period from 1992 until 2003 have experienced strong ground motions. And I think that I will now go through the story. 1992, magnitude 6.6. There have been reports of the same earthquake with a magnitude of 6.8 in various publications, but a 6.6 earthquake at an epicentral distance of a few kilometers surely represents a strong ground motion. Next, 1999, different geographical location. Look at the similarity of the two buildings. They are in fact identical. The reason why the Erzincan earthquake, the Erzincan building looks slightly different is because some retrofit had been done, but the building experienced the 1992 earthquake in its original state, which is represented by the 1999. And finally, again, the identical building that experienced 12 years later a 6.3 magnitude earthquake. Now, what makes these buildings and the damages that were recorded on, none of them collapsed. One of them was damaged pretty badly and it needed to be raised to the ground. The 1999 Düzce earthquake damaged the building, so it needed to be demolished, but they did not collapse. They're all identical and they represented the provincial services building of the Ministry of Public Works. Now, the ministries have built facilities in various provinces where the provincial services with which that ministry is charged with are carried out. Now, the particular property of these buildings is that the ministry places their strong motion stations on near the same building. So we know exactly the ground motion that those buildings experienced, except the one in Erzincan, 1992. The distance between the building and the recording station on identical local geological conditions was 2.4 kilometers. So we will make the simplifying assumption that the ground motion in Erzincan was what the building experienced. The objective is, well, given the benefit of hindsight, could anyone have predicted the response and the damages of these buildings? Now, the instruments were on the ground, adjacent to the building. There was no instrumentation at all in any of the three buildings. So we don't really know what drifts, what motions the floors of the buildings underwent. But we do have extensive recordings of the damage. And damage perhaps is one way of going back and making reasonable estimates of the forces or drifts, displacements and strains in those buildings. Now, the typical building is shown here. It's ground level plus 4 regular stories. There are usually adjacent buildings, but this building, the one that is marked in red here, was identical in all of the 3 cities. No shear walls, but oversized L-shaped corner columns in all of them existed. The rest is regular moment resisting frame. And here it is. The oversized corner columns, and then these ones, and this one is missing, and then a number of girders, the peripheral beams, the interior girders in the north-south and east-west directions, and then the oversized corner columns, the longitudinal columns, the interior columns, and finally the transverse columns. Now, because of the identical nature of the design, all of these buildings had exactly the same columns and exactly the same reinforcing details. All right. Here are the material properties that were retrospectively established. The ground motions were pretty severe. In 1992, the 2 components were of the order of 0.4 to 0.5 Gs. In 1999, they were of the order of 0.75 to 0.8 Gs. And in the year 2003, they were of the order of half a G in one direction and 0.28 Gs in the other direction. And the other indicators of the ground motion are listed here. All of them correspond to pretty strong ground velocities, which is, of course, the driving parameter of the ground motion in causing damage. Well, the heaviest damage took place in 1999. These are captive columns at the end of the transverse interior frame, and they were all sheared. No ifs and buts there. But I think that a strong case could have been made for the fact that these were captive columns, increased shear, etc. The ministry took the contractor of the Bolu building to court. The court case dragged on for a number of years. I think that the contractor was not guilty in terms of negligence. He built what was given to him. The response of the building was more or less what could have been expected of a 0.8 G ground motion damage, and the building stood, no life damages. And still the ministry not to be blamed for using a damaged building, a heavily damaged building, at a later date, decided to pull down the building and replaced it. And the Erzincan building, the one that experienced 0.5 Gs, seemed to experience the least severe damage. Now, we then went to the arsenal available to earthquake engineers, pulled out all the weapons, given the ground motions, given the material properties, given the building sizes and dimensions and so on. The expectation was that we could more or less predict the observed damages in all of these buildings. Of course, the columns were all shear sensitive, so we made an estimate of the shear capacity of the columns, given the response, given the forces, the drifts at the tops of the ground level columns. It is reasonably possible to estimate the moments from the drifts and from the moments the resulting shears in all of them. And does that shear correspond to the damage that we visually observed in all of them? Now, the base shear, in terms of the weight of the building, in the two directions of the building, were of the order of 0.25 to 0.3, maybe 3.4 of the weight of the building. Now, this is, of course, a pretty heavy amount of base shear. The buller, the one that was most severely damaged, seems to have possibly experienced a base shear of the order of 0.3, 0.34 times its own weight. And the cross-sectional area of the columns above the base divided by the plan area at the base, the floor, seems to was in all of them, of course, 0.5%. Not adequate, but of course that's only hindsight speaking. We made an analysis both for flexure as well as for shear for the columns. We looked at the infill walls. We made use of the models that have been recommended in the ASC 41 and ASC 7 formulations. And we even were lucky or unlucky enough to experience a minor earthquake while we were visiting the building in Bingöl. We were able to record it for making a Fourier analysis to see what the period was, and the period seemed to be pretty accurately predicted by our analytical models. Right, so it wasn't too bad. We looked at the roof displacement predicted from the performance-based software that we were using, and the roof displacement also did not appear to be excessive. Well, here are the predictions in the case of the three buildings. The Bingöl building, which was the least severely damaged, was expected by our analyses to experience a 1.5% roof drift, but that does not agree at all with the damage that was observed in that building. Whereas the Bolu building, which experienced analytically a drift of 1%, was indeed badly damaged, and as I have said, needed to be pulled down. We did pushover tests, analytical tests, numerical tests, and that seemed to confirm the analysis on the basis of the shear capacity that we had already done. The story drifts, and finally the evaluation at member level. Right. These damages, of course, were caused by the captive columns, and it is very difficult to make a rational analysis of a captive column because it depends heavily on the confining walls, of which we did not know the properties all that well, but they seem to have had enough capacity. The girders, the crosses indicate mismatch between the analysis and the observation. The check marks indicate agreement between the damage in the corresponding member and the calculations. Infill walls, the performance calculations wasn't that bad, and I have already spoken at length about the predictions concerning the columns. So the sobering lesson that we learned from the experience on these three buildings over the course of 12 years seems to indicate that we need to develop finer tools, finer predictive equations for damage. Now, damage, of course, is heavily in the nonlinear range, and it is difficult to make much heads and tails of damage. And I recall in this connection the extensive testing that was run at the University of California, San Diego, on that shaking table on a 7-story model, and the predictions that were made on the basis of the geometry, the material properties, and the other details of the 7-story model, full-scale, nearly full-scale model. Well, some teams were badly off even there. So before we can make predictions of monetary losses caused by the 2,475-year earthquake, which nobody has experienced, of course, for the benefit of the insurance and the reinsurance industry, I think we should be sober and admit that we have a long way yet to go in that respect. I believe that this is my last slide, but I have already vocalized what the conclusions are. So, ladies and gentlemen, I thank you very much for your attention. I'm afraid that this is a somewhat negative conclusion slide set, but I think it is also beneficial to be modest in our claims. Thank you very much.
Thank you, Polat Hocam, for this nice presentation. And are there any questions at the moment?
Hi, Alp. It's Khaled Mahmoud. Thank you very much, Professor Polat. It's a very, very informative presentation, and we appreciate you for that. I would like to ask you, after the late 90s, I think it was 1999 earthquake in Istanbul, there has been a wealth of knowledge and developments in the seismic area in Turkey. What did stand, in your view, what stood out of the Izmir earthquake and the catastrophe that happened there? What did stand out? What surprised you the most about what took place there?
Well, is this Khalid?
Yes, this is Khalid, Professor.
Well, nice to see you.
Nice to see you, sir. Thank you.
Well, the lessons, Khalid, that these earthquakes, including the experience in Istanbul in 1999, points first and foremost to the fundamental errors that the community of civil and structural engineers in this country commit time after time. Only 2.5 weeks ago, there was a strong earthquake in Izmir, and 6 buildings, 6 multi-family condominium buildings have collapsed there, killing a number of people, 116 in fact.
Yeah.
Now the fundamental lessons, the things that we think we are advising our students and our colleagues against, build strong columns and weak beams, seems to be ignored in each of these cases. Basic error.
Yeah.
Build, because it's not going to cause any appreciable cost differential. Build shear walls whenever and wherever you can. That is not done. So the lessons that stand out are actually lessons that we have learned and many times over again. We really need a decently built, a decently designed and constructed building that experiences a strong ground motion in this country for us to derive from it lessons of enduring value for the benefit of others. That has not happened. And the few cases involving tunnel form buildings that I have personally observed and inspected point to the fact that tunnel buildings, no columns, all walls, are wonderful, but they cost not all that much, but you spend a lot of money for the foundation system because those buildings are heavy to begin with.
Yeah.
But if you want to save lives, go tunnel.
Yeah. But
that's the lesson.
one important element here is that what you say is very true, Professor Polat. So how come this is not given teeth in the specifications? If that is the conclusions of experts such as yourself in the seismic area, how come this is not given teeth in the specifications that engineers must follow this kind of protocol in the design and the construction?
Thank you, Anil. Let me make an addendum to what I've just said. The 6 buildings that collapsed 2 weeks ago in Izmir had all been designed in the 1990s according to the 1975 code. And the 1975 code is not a faulty code.
Mm-hmm.
Actually, it's not a code, it's a regulation. It's slight difference in there. But if the basic principles of good design had been observed even there, abiding with the requirements of the 1975 code, those buildings might well not have collapsed. Now, we have a code today in effect. It has gone into effect in the beginning of last year, 2019. We do have strong requirements for the building, for the insertion of shear walls there. But any code, any regulation that you bring in today will show its colors, its benefits 20, 30 years from now.
Yeah.
Not immediately, not overnight.
No, of course, not immediate. Yeah, of course. Yeah. Very good. Thank you.
Thank you, Polat Hocam. Are there any questions from the audience? Thanks a lot, Polat Hocam, for all your support for this 2020. It was very difficult for us to do, for sure, this online conference, but I think at some point we managed this, and when it started, I know that there are about 200 people watching us, and it's a long time because of all these time differences. And so usually a conference doesn't end in 8 o'clock, but in Turkey. So we have to extend, and thanks for all your support, basically. And I'd like to also thank to the staff who made this possible. I will just turn the screen like this, if you can see them. And they are here. They did this possible. Like Mustafa Can has the technical support, and Meliken having supported the conference, and Dilara and Damla take care of all the correspondence and all the emails and make this possible. And I would like to thank them on behalf of you. And yeah, we just waiting for 2020. They are very eager to do that in face-to-face in Istanbul, hopefully this time. And thanks for all attendance, basically.
Alp, if you allow me to say on behalf of all the participants, and I think everybody will second me, I commend you and commend your staff for a job very well done. And you almost competed with the fact of being in Istanbul, but let me say that we would love to be in Istanbul next time. And we thank you very much for this event. You've done a great job. Thank you.
We couldn't manage Hilton, but I know you like Hilton.
It will be a pleasure to come back to Istanbul soon, inshallah.
We tried, Khalid, to deal with Hilton, but we couldn't. Like, the better option for us. And and again, I'd like to thank Mustafa Can, Melike, Havin, Dilara, and Damla. They made all this possible. I mean, because there were lots of glitches during the conference, and at some point we lose the conference, and then all of a sudden we catch it. And thanks a lot.
You guys pulled it off, and it's a very good job. Thank you very much. It's a pleasure to see you, Professor Polat, and look forward to seeing you in person again soon in Turkey.
Thank you.
Thank you.
Thank you. And have a nice weekend. Or
I think you guys need a break now. It is your weekend. Not a very long weekend. Thank you. Good job. Take care.
Bye now.
İyi akşamlar.
İyi akşamlar.